So a lot of, especially in the beginning of this class, we are going to be using one particular equation for a lot of the discussion of our numerical techniques. That's called the convection diffusion equation. The convection diffusion equation, if you write it down, is let me call W being a function of x and t is the solution. You mean this set of notes? Yeah. Sure, I can. Right. Oh, another thing is I try to record the lecture, and if you happen to didn't pay attention to some of the lecture and want to go back and listen to me again, you usually can. Just we try to publish the recording to YouTube, so it takes some time to process the videos, but after maybe 2-3 days, you can go to YouTube and look at the lectures. Okay, so let's say W is a function of x and t, so it's the solution to the following equation: partial W, partial t, okay, plus a velocity times partial W, partial x is equal to a kappa, which is the diffusion coefficient, times the second derivative of W with respect to x. So this is an equation with 3 terms. The first term is an evolution in time. So that's the rate of increase of W at one particular point. And this is called the advection term. It's proportional with a proportional constant u to the first derivative of W with respect to space. And we can look at the behavior of that term. And the third term is the diffusion term. Diffusion term is also proportional to W, its second derivative in space. And we can also look at the behavior of that term. All right, so let's first gain a little bit of intuition about the behavior of this equation. And then we can start to use analytical method to figure out why it behaves that way. And the reason we choose that equation is because of its diverse set of behaviors, right? So we can use it as a pretty typical example to study 3 different kinds of equations that has very wide applications. And 2 is that this equation actually is amenable to analytical methods. So we can derive analytically how the equation is supposed to behave so that we can check our numerical solution with the analytical method. But as soon as we start to develop numerical method, you are going to see that the numerical method we are going to develop and verify and test on top of this equation is applicable on far more than this particular equation. Right? But this is basically our playground for our numerical method. So first step is to establish our playground. So I have a function convection diffusion equation that is going to be showing the solution to this equation. And I have 2 arguments. The first argument is this big U, and the second argument is the kappa. So let's first test how the solution would look like if I have some non-zero U but a 0 kappa, so 1 and 0. Okay, so when I do this, I get a screen that is blank. So that is a drawing ground for the initial condition of this equation. As you look at this equation, this is one of the equations that is time dependent, right? We have a time as one of the independent variables in this equation. And this type of equation usually requires a prescribed initial condition, just like our weather forecast. You wouldn't know what the weather is like tomorrow unless you know what the weather is like today, right? So if the weather were different today, the evolution would take a different path. So that's a typical situation when you have a time-dependent partial differential equation. So I like to have somebody who come up and just draw the initial condition for that advection diffusion equation.